Okay, we're going to do something that's rather ambitious, right? In about an hour to do an introduction to general relativity, obviously it's impossible. But luckily, you've already taken a course with Eduardo. And so I'm going to assume, on the one hand, that you know certain things. I'm not going to have to explain it. And also, I'm going to distribute sheets, which I'll expect to be able to kind of walk through in a very few minutes, rather than spending an entire hour explaining. On the other hand, I'll do exactly the opposite. I'm going to ask you to pretend that you never learned general relativity and don't even know about special relativity. Because the object of the game here is to see how much of GR we can actually heuristically motivate from Newtonian gravity. So I'm going to try to do it a little bit interactively, to ask you questions, to try to prod you to give an answer. But I want your answers to come from your knowledge of general dynamics and Newtonian theory and so on, not from your knowledge of special relativity and general relativity. Okay, now what I'm going to do is heuristic motivations. In other words, I'm not saying that you can derive from this way, nor am I claiming that some super genius in Newton's time, Newton himself, ought to have arrived at general relativity. It's very much in hindsight. After we already know Einstein's theory, and after many, many people have elucidated it over the century, basically, since then, in hindsight, we can look back and discover in Newtonian gravity many of the deep ideas that we usually associate to general relativity. Okay. Now, I'm going to do something that's a leap of imagination. All right? And I'm going to say, what happens if I do something funny, a little bit strange to space-time? I'm tempted to use the word curved rather than warped for this space-time, for the simple reason that the world lines uncurved or became curved. I'm deliberately not using it for reasons that I'll explain afterwards, and I'm going to talk about just warping. I want to now use the word straightest line in a warped spacetime, the general term geodesic, because it's not just an ordinary straight line. It's not even a straight line in spacetime where we just have these two perpendicular axes and so on. We have something very odd. So the question will be, can one use the same terminology, right? And if we investigate in mathematics, it finds out that in fact we can. And it's partly a matter of definition. I'm still not sure if it's definition or if it's a miracle. I don't know. It may be just a matter of definition. So now, what is the law of motion that we're expecting? In an unwarped spacetime, obviously inertial particles are geodesics, right? They're straight lines. In a warped spacetime, are they geodesics?
Yes.
Two yeses? No? No?
Maybe.
All right, we can define an inertial particle world line as the world line, which is a geodesic, and it intuitively makes sense. We'll say an inertial particle is has a world line which is a geodesic of this warped spacetime. All right? So now we have a law of motion. We don't have a field equation. We don't know how this warping takes place or why, but we know what we expect as a result of any kind of warping. Again, inertial particles have geodesic world lines in both a warped spacetime and an unwarped spacetime. I want to now use the word straightest line in a warped time, curved spacetime, something. This is the general term geodesic. Correct? Right, that's our theory. So we know that the acceleration equals gm over r squared. That's simply the curvature of the world line in flat spacetime, nothing exotic. Okay, purely Newtonian flat spacetime, whatever that means. Right? That world line curvature will be something more complicated than it's reduced to. I'm tempted to use the word curved rather than warped, for the simple reason that the world line's uncurved, or became curved. I'm deliberately not using it for reasons that I'll explain afterwards, and I'm going to talk about just warping of time. And afterwards we'll, because again the word curvature has very specific meanings. Okay? So now we're motivated to look in gravity and see, do we see some features that, that hinted at this? Now, one of the features of gravity that's unique, of course, the one that we mentioned before was the equivalence principle, right? As part of that, if you're falling along in a free fall frame and you see any other freely falling particles, of course, doesn't mean only something that's literally falling, as you say in English. It means something upon which nothing is acting other than gravitation. All right? So it can be a projectile going up. It could be something orbiting. Those are all in free fall. Correct? If you are in free fall, in some free fall state, and there's a bunch of other particles in free fall, in all kinds of different free fall motions, but all of them in free fall, what will you notice about their motion? Let's say they're crossing your path. There's an orbit. You're been ejected from the Earth, all right? And you're on this kind of trajectory like this, and there's a particle orbiting right past you, and there's something going up and down, and all these particles, they're all kind of converging, not quite hitting each other, passing by each other. What do you notice about their motion? What does their trajectories look like to you? Not even a world line. Straight line. Because you all have the same acceleration. So you've wiped out all the acceleration. All you're left with is velocities. They have different velocities relative to you, but they don't have acceleration relative to you. Okay? So that is something very unusual, and that already hints at ideas of it being a geodesic. Somewhere there's a geodesic hidden. Another thing, if you have, let's say, an electric particle in a magnetic field, electric field, and you shoot it out at a certain angle, okay? What do you need to know, given the angle? Do you need to know anything else to be able to map this trajectory?
Something about doing stuff. The acceleration could be different because there are different distances from different.
Yes, right. Okay, that's right. Right. If you're talking about particles that are right near each other, they should all have the same acceleration. But we need a field equation to determine what is causing this warping and how does it affect things at different distances from whatever source it might be. So I would be talking about things that are right near you. Okay, and in this case, just in ordinary gravity, things right near you. So I notice they're straight lines. Now, if I take a trajectory of a particle this way, like this, is that sufficient to map the rest of the trajectory? An electric field. What?
You need the velocity.
You need the velocity. Right. You might need an electric field. You might need, the mass, the charge ratio. All kinds of things to get things going. In gravity, though, is it or isn't it not enough? if I know the initial trajectory.
You ask for free fall, for free falling.
Yeah, there's only, well, it's not a free fall. Let's say I'm right here on the planet, and I'm ejecting the particle at an angle.
You know the velocity?
Pardon me?
You know the velocity?
Sorry?
Do you know the velocity?
Okay, so the question is, what do you need in order to map out
Oh,
the...
yeah, you need the velocity.
You need the velocity. Okay, is that sufficient if you knew the velocity?
And the angle.
And the angle.
The angle, right? You know the orientation. If you know the velocity is a vector, so you have the angle and the amount.
The initial side, the initial
Okay.
velocity.
Would you know the rest of the... Could there be several different particles with the same velocity and they have different trajectories?
No.
How about if it's an electrical particle in an electric field? Yes. So gravity, part of that uniqueness, another way of looking at it, is that if you have the initial tangent to the trajectory, you can entirely specify the entire curve. That is a property of geodesics. It is not the trajectory which is a geodesic, of course. Okay, it's the world line. But these are hints in gravity. Something is going on here. There's straightness locally, local straightness. The lines are straight even though they're not supposed to be their curved trajectories, and yet I see them as straight lines, all these other particles. And I can uniquely specify the entire trajectory given an initial tangent. If you knew about differential geometry, you would say, that's basically the definition of a geodesic. We'll say an inertial particle has a world line which is a geodesic of this warped spacetime. Now we discovered that this should describe gravity. All right? So now we have a law of motion. We don't have a field equation. We don't know how this warping takes place or why, but we know what we expect as a result of any kind of warping. Okay? So we have this one sentence which is kind of morphed and taken on much, much more significance. Again, inertial particles have geodesic world lines in both a warped spacetime and an unwarped spacetime. So look at what we've done to the inertial law. Okay, the law of inertia. We started out with a law based on trajectories. We said an inertial particle can be a point, a dot trajectory, or it could be a line trajectory, nothing unique about that. We went up one level and we said an inertial particle has a straight world line, and that's it. That's a unique definition and takes into account stationary particles, moving particles, everything else. Very, very nice, right? Law of inertia, inertial particles have straight world lines in this spacetime. We've now taken the same words, inertial particles have geodesic world lines, and it's true even for a warped spacetime. We spoke about this law of inertia that applies even to warped spacetime, right? Now we see, what is this law of inertia for warped spacetime? What is it really? It's a law of what? Geodesics. And it describes what natural phenomena? What natural phenomena does it end up describing? Acceleration of gravity. All right? So instead of talking about acceleration of gravity, we're going to say that particles, even in what would have thought of as a gravitational field in the presence of matter, there is no such thing as gravity, gravitational field, you know, acceleration, all that kind of stuff. These particles are inertial. They are inertial particles. The Earth is orbiting the sun. The Earth is an inertial particle. It's not acted on by force from the sun. It's not accelerating as a result of the force of the sun. It's an inertial particle. However, the Space-time is warped. An inertial particle has a geodesic world line. It's a geodesic of the space that it's in. If it's a warped space-time, then the geodesic is not the ordinary geodesic that you would expect from just flat space-time. Okay? So we can totally get rid of the whole notion of gravitational force and even gravitational acceleration. We have inertial motion, and that's it. Inertial motion, being a geodesic of space-time, makes total sense, even if space-time is warped. In which case, what we will see, remember this picture, the guy opens his eyes and didn't know the time was warped, what we will see is accelerations, and strangely enough, we'll notice that it's mass-independent and velocity-independent and so on. That phenomena that we see as mass-independent, velocity-independent accelerations is exactly this, geodesic inertial motion in a warped spacetime. So now, we need a little bit of mathematical structure to figure out what does it mean to say that these lines became uncurved and became straight in a warped spacetime. Is there any meaning to that? I started out with a straight line in space, which we know what that is. I then defined a straight line, a geodesic in space-time. And we felt comfortable with that. What is a geodesic of this warped time, curved space-time, whatever it is?
Couldn't I think of it just mathematically? If I have any line in space-time, then any small part of it is a straight line, so it's inertial.
There's a difference, though, between straightness and geodesicity. Okay, this is a subtle thing that has to do with limits also. Obviously, any curved line, if you look at it close enough, is straight. All right? Nothing complicated about that. But there is. If you look at the limits, then one thing goes faster to zero than the other thing, and so you end up seeing it straight, and that's what curvature means. All right? In terms of straight. But a geodesic is a special path in a curved space or surface. Right? You can have a curved surface, and you have any curve, that will be true, that if you look at it, it's like a straight line. But the geodesic has special properties, more than just any curve. For example, this thing about the tangent that you can transport the tangent along itself and it doesn't change. Okay. Now, at this point, though, we really have to do a little bit of math. If you take the equation of a straight line, okay, just in yx, so you have straight line is y is equal to mx plus b, right? M is the slope. First derivative of that, y prime is equal to m. Y second derivative equals to 0. So the differential version of the straight line equation, instead of y equal to mx plus b, would be, let's say, y double prime is equal to 0. Okay? Now, how about if we're on a curved surface? Just an ordinary curved surface. No space-time, nothing. Just a curved surface right here in the room, right? One of these chairs. Can we define a straight line? Now, clearly, it's not going to be the straight line, in the rest of the room. We're talking about a straight line if we're restricted to the surface. Is there such a concept? It turns out that it can be rigorously defined. It has to do with taking a tangent and then parallel transporting it and continuing it. It's the same. Or maybe you've learned about it, maybe not. We can also do it, the same thing. Let's take, first step, a straight line into an ordinary xy coordinate system. And I have y equal to mx plus b, or y double prime equal to 0. And now and I have a physical straight line that I'm describing. I'm now going to change my coordinate system. Right? I only need 2 dimensions. Let's say I'll take polar coordinates r and theta. So I have r axis and the theta axis, circles. Being perpendicular everywhere, they kind of slant around. Right? Is theta double prime a straight line? So now, clearly, you're going to have a description in this coordinate system. It can't be that you made a polar coordinate system and you can't describe mathematically what a straight line is. But also, very clearly, it's going to be more complicated than just theta double prime equals 0. In fact, r is going to creep into that equation. Right? You have theta double prime plus r, whatever, all kinds of things like that coming in. All right? So now I'm just going to say a little bit about the math. What is a connection? A connection is a property of a space or a description of that property. It's used in different contexts. If you talk about a straight line in straight space, okay, is there a connection just on regular 3-dimensional space, our physical space, if we didn't know about spatial curvature and stuff? No. Okay, and the answer is yes, or maybe. How do we know that there is a connection? Because if you describe a straight line in Cartesian coordinates, right, it's just so we can define a straight line, but some other things creep into the straight line equation. Right? Those things are called connection coefficients. It has to do with how the coordinate axes are related to each other, not equals 0. If you describe it in polar coordinates, it's complicated. Those things, those little complicated things in the equation are the connection coefficients. So the connection coefficients tell you how to describe straightness and define straightness whenever there's curvature. It could be curvature of coordinate lines where the thing itself is as flat as can possibly be. It's a straight line on a flat surface in a flat space. Or it could be that it's describing how a straight line, what a straight line is on a curved surface, so that's already more abstract. Or it could be that it's telling you how to define a straight line in a curved spacetime or work space. In mathematical terms, you would say that a straight line, or the collection of all straight lines in space, is the connection on space. What is the connection on space-time? If the collection of all straight lines in space is the connection on space that defines straightness and parallel and so on, what would be the connection on spacetime, just ordinary flat spacetime? Would be the collection of straight lines in flat spacetime, which are inertial particle world lines. So inertial particle world lines, the collection of them is the connection on flat spacetime. What's the connection on curved spacetime, warped spacetime, as we define it?
Acceleration?
Okay? Again, the connection is the collection of straight lines in space, connection on space. The connection on flat spacetime is the set of inertial particles. Inertial particles are physical things moving with a certain dynamic. We're talking about spacetime, it's a physical thing. The collection of all those inertial frames or inertial particles is the connection on flat spacetime. It defines straightness. What defines straightness? What's the connection on curved or warped spacetime? Collection of all geodesics of warped spacetime, which are, in physics terms, white constant, GM of R squared is not constant. So free fall particles. Particles that are only under the action of gravity, not under anything else. Those have geodesic world lines. And therefore the collection of all free fall particles or free fall frames or the world lines of free fall particles defines the connection on curved spacetime. Okay, that's like a more mathematical way of saying what we said. All right? Now we can call these free fall particles inertial. So really, again, we can just say the collection of inertial world lines defines the connection on spacetime. And if we mean a curved spacetime, then it's inertial particles meaning free fall particles, same thing, and warped spacetime. It's the same sentence. Just like we had before, inertia, the law of inertia was inertial particles have straight world lines, right? The same thing we're saying, the connection on spacetime is inertial particles, where we already know the subtlety. That it could be, we mean free fall particles in a warped spacetime. All right. All right, have you all seen the geodesic equation? So you know what I'm talking about, right? You have the second derivative equals to a gamma times, is there something who hasn't seen? I'll just show it to you on the papers or show it right on the board. So, everybody seen it? Okay. Components of the connection give you all the information that you need to write this straight line equation, even in curvilinear coordinates. So we can construct a theory which tells us, despite the curvature of the coordinate lines, what is the equation of a straight line? And it turns out we can use exactly the same definitions for a curved surface. All right, we have coordinate lines on the curved surface, and we can define a straightest line on that surface, and it has exactly the same format. You're going to have a second derivative of a coordinate, and then you're going to have other terms coming in, and that equals to 0. Now what we're going to do is apply it to space-time, just regular, ordinary, unwarped space-time, right? We'll just do the same thing, and I'll define my geodesics of space-time. So it'll just be, let's say, r equal to at plus b, right? Or t is equal to ar plus b. All right? I'm just defining a straight line, and I'm going to define it that way. And if I have a warped space-time, I'm going to define my straight lines in exactly the same way that I defined them for curvilinear coordinates on a flat plane in a regular flat space, and exactly the same way that I defined it for a curved surface. I'm going to, and exactly the same way that I generalized that for the new space that we call space-time, I'm going to use the same formalism to define what it means to have a geodesic in this warped space-time. Okay? We're going to have a geodesic equation in a curved space-time. The geodesic equation is going to have r double dot equals a bunch of gammas. Okay, that's the geodesic equation. That's going to somehow reduce down to r double dot equals gm over r squared. Correct? right? That's our theory. So we know that the acceleration equals gm over r squared. That's simply the curvature of the world line in flat spacetime, nothing exotic. Okay, purely Newtonian flat spacetime, whatever that means, right? That world line curvature will be something more complicated than reduced to. With all the gammas, we'll reduce to this world line curvature. We had a straight line equation which we developed and kind of morphed into a geodesic equation even for warped space-time, etc. All right? Now, this equation, since it's based on the differential variant version of the straight line equation, has in it a second derivative of a coordinate. Okay? And the geodesic equation will be the second derivative will be equal to a bunch of stuff instead of 0. And the bunch of stuff has to do with the connection components. Correct? We have this maybe long equation and stuff like that. That's the equation. When we say that's the geodesic equation, what is that really describing? It's an equation describing geodesics. Does it describe the geodesic itself, so to speak? Let's look at just ordinary flat space-time like this, RT. What would be the equation of the geodesic? It could be R of t, right, is equal to AT plus B. Right? That is what we would think of as the equation of the geodesic. The differential version of it, in terms of the differential equation, would be second derivative is equal to 0. Right? But that's already an expression of the curvature, the vanishing of the curvature for a straight line like this. And if you have a warped space-time or a curved surface or curvilinear coordinates, you have a vanishing of the curvature of the line, but because of all these funny things happening to the coordinates and so on, or to the space or the surface, you can have other terms. So it's not just going to be second derivative equals 0. Second derivative plus these other terms that depend on the connection equals to 0. All right, so it's really a description of the curvature vanishing, because by definition, this is a straight line. Okay? So you see, you have to be kind of careful with the terminology, because you have this geodesic equation which is describing a geodesic which by definition is a straight line in that space. You can't say, well, it's the straightest line that you could possibly define, but it's not really straight. No, it's straight. You're in that space, and this is a straight line, and this is the description. All right? How do we go about constructing the theory of gravity now that we know that that's what it's going to be, based on not only space-time, but this warped space-time? Okay? Now, let's start looking at the theory of gravity. All right? We'll take a spherically symmetric source, meaning that the density is spherically symmetric, and therefore the shape. I'm going to be outside and not inside. I'm going to be in vacuum. Afterwards, I'm going to specify that we're talking about a local theory. So the source term in my field equation inside the mass could have a density, outside the mass it could be 0. I'm going to need to match boundary conditions and so on. And if I look at the gravitational field, what can I usually learn, F equal to gmm over r squared, right? I can get rid of that because that's unnecessary and actually hiding the essence. Why?
Except mass is not that important.
Say it again?
We say that mass is not important.
Right. So what should I have instead?
But you can't say if your mass is 0 because...
No, my source mass is not 0.
Yeah, no,
The particle mass.
the particle mass.
Right.
Because it's like multiplying by...
Okay, yes, But we can do without the mass altogether. We define an acceleration equals to gmm over r squared divided by m, assuming that the inertial mass is the same as the passive gravitational mass, and so on. They cancel out. And you end up with acceleration. What we're going to do, so we don't have that problem, is we're going to define an acceleration field outside this mass. At every point outside this mass, there is a specific number with a direction, right? I'm going to forget about the direction because it's obvious. I'm just going to talk about the number. It's spherically symmetric, right? At every point in space, there is a specific number telling you what the acceleration is. If you have particles moving with all kinds of different velocities in different directions, every single one will have exactly the same acceleration at this point. Correct? Is that true about any other force? Can you do this with any other force? No. Because what you have for other forces is exactly that, a force. You don't have an acceleration, you have a force. To find out the acceleration, you might need the mass-charge ratio and all kinds of other things. It might be velocity-dependent, etc. Only for gravity. So for gravity, we can define an acceleration field. Which, right away, even if we didn't do anything more, that's a beautiful idea. Okay? And it makes it very intuitive that all these particles will have exactly the same acceleration. Now, before we saw what is acceleration from the space-time perspective? It's equal to
Curvature.
world line curvature. So we can, if we want, talk about a world line curvature field. We didn't gain anything, it's just kind of a nice idea. At every point outside this mass, there's a world line curvature field. Pardon me?
How do you assign the acceleration field for the space-time?
Okay, the acceleration field is really in space, but if it's a static source, all right, then I can just take it at any one time and it's representative at all times.
So it's the same for.
Right, I can draw the world line of the particle. I just take a, I know its acceleration at any point, I know its velocity at any point, I'll just draw its world line, whatever it is in a space-time diagram. Nothing is changing with time, so I can talk about a region of space just as easily as I can talk about a region of space-time. But the thing that we're interested in, the creature of interest, lives in space-time. It's the world line. Okay. Any particle whose world line is at that part of their world line, so to speak, is at that point, will acquire a curvature given by this specific event. All right? Now, though, we want to go one level up. We want to see that as a shadow, as an image of something else. Okay? Where does this world line curvature come from? We came up with this model of a warped time within the concept of space-time, right? And somehow that's causing these world lines to curve or uncurve and so on. Correct? So now, going back to the math a little bit, we want to map this acceleration field, which is really a world line curvature field, to something that has to do with the ultimate cause of it, which is time warping, space-time warping curvature, whatever it is. Okay? How are we going to map those two things? What should we look at?
Okay, the time axis.
Okay, that's one thing. But let's say in terms of something that I spoke about before, and I don't want to give away again the answer by formulating the question too clearly, but we want to somehow map the mathematics. All right, we want to take everything that we said and find out what do we expect mathematically. We have a law of gravity. We boiled it down basically to A is equal to gm over r squared, where m is the source mass. How is that going to pop up in this warped space-time theory? Where is that going to appear?
In the curvature or metric of time or something like that.
Sorry?
In the metric of time or the curvature of the line or something.
Okay, so I'll go with it right now. Afterwards, we'll do that other thing about the time. We'll go with the curvature of the line. Say it more explicitly. Someone else?
The amount that the lines are going to curve.
Which lines?
World lines.
Okay, as a result, which world lines? Just like try to make it explicit.
So that's
But
the six.
geodesics, okay. Make it into a sentence. No, it's difficult. It's not simple because you have to get the concept. Like, it's good. Go on.
I'm gonna let you.
I was hoping there's something, I don't know, I don't know the answer. Okay. If we were looking at curvilinear coordinates, it would be the curvature of the coordinate lines. If we were looking at a surface, maps to what we would have called the curvature of the geodesic, but we can't say that. It's not curved. So it's not really the curvature of the geodesic. If we're in a space, you can say maybe the space is curved, but the geodesics are by definition straight. Okay? So yes, we expect that this acceleration, which is world line curvature in the flat space-time view, maps to what we would have called the curvature of the geodesic, but we can't say that. It's not curved. But what it does map to is something in the geodesic equation. You're going to have a geodesic equation. Instead of r double dot equals 0, you're going to have r double dot equals a bunch of stuff. And you're going to expect that that's going to boil down somehow to what?
Curvature of time of the axis.
Something that we know. What were we looking for?
Now, r double dot equals something.
Right. And we know we're doing a model of gravity, so we know that in the end we're going to get what? R double dot equals plus minus whatever gm over r squared. So somehow we expect this r double dot equals gm over r squared to pop out of this big geodesic equation. Correct? Out of these connection coefficients and so on. Okay? But basically we have this intuition, we have this idea that what we're looking for is a geodesic equation with a whole bunch of connection coefficients that's going to boil down to r double dot equals to gm over r squared. We know that this world line curvature, though, is actually a shadow of something, right? The world line is curved or uncurved because really it's a geodesic. And in the geodesic you have connection coefficients, which are going to boil down to this gm over r squared, this curvature. So this gm over r squared is really a shadow of something to do with the connection coefficients in the curved space-time theory. All right? We know that in the flat space-time picture, it's a world line curvature. That's simple. It's just calculus. Draw r of t, and call it the world line. The curvature of that world line is simply the acceleration. Okay? So we can write, if the connection components are these gammas, we're going to write the shadow also, just as a simple, we're going to write it as a gamma. But instead of having 3 indices, we're going to write it with 2. Okay, this is my own notation. It's not standard notation. It's just a symbol. All right, it's not a geometrical object that's well defined. It's the shadow of a gamma in the curved spacetime. Okay? Intermixing the r and the t. All right?
Can you explain again what does
Sure.
it have to do with
Yeah. We're going to have a geodesic equation in a curved spacetime. the geodesic equation is going to have r double dot equals a bunch of gammas. Okay, that's the geodesic equation. That's going to somehow reduce down to r double dot equals g over r squared. With all the gammas, will reduce to this world line curvature. Okay, so I'm calling the object that it reduces to this gamma with gamma RT with two indices. It's simply the world line curvature. Okay? It's a world line curvature, but we know that the world line curvature is a shadow of something that's happening in curved spacetime, and the thing that's happening in curved spacetime are these gammas in the geodesic equation. So again, we have this geodesic equation with gammas. We know that that gamma is going to show up in this flat spacetime as the curvature of a world line. So I'm just labeling the curvature of the world line since there's no symbol for it. I'm going to call it a gamma, but instead of 3 indices, I'm going to call it gamma with 2 indices. So it's not the same as the gamma, it's just the shadow of all these gammas in flat spacetime. So now let's try to write this geodesic equation. All right? We're going to have now a space-time geodesic. So it's not going to be just 3 dimensions of space. We're going to have 4 dimensions. And we want to, for reasons of covariance, which is a different thing, and we want to treat all these dimensions equally in the same way. Even though we know time is kind of special, but we're going to treat them mathematically in the same way. So one of the things that's not going to be possible, for example, if we had r double dot, second derivative of r with respect to t, we can't do that. We can't use time now as the parameter with which we're taking derivatives. It's part of the dimension of the theory. In fact, we're even going to have a geodesic equation where on the top it's going to have second derivative of t with respect to something. You have second derivative of r, second derivative of theta, second derivative of phi, you can have second derivative of t also. All right, so we're going to have to define a parameter with which we're going to take, with respect to which we're going to take a derivative. All right? How are we going to get that to look like r double dot? If we can't use time in there, how are we going to get that to look like r double dot? How's that going to boil down to the left-hand side of the equation of gravity that we're trying to get? Any guesses? Yes, no, maybe? Time is a coordinate.
Yeah.
I can't. Which time do you mean?
It means the second derivative with respect to the parameter.
With respect to a parameter. Okay, so which parameter? But how are you going to get it to look like the equation where time is? Time is definitely going to be in there somewhere. It's going to boil down to second derivative, let's say r with respect to t, in order for us to make contact with the law of gravity. How are we going to do that, though? How are we going to take a second derivative with respect to a parameter and get that parameter to be t?
Respective to the speed of light or something?
We don't want to get into special relativity as much as possible. Okay? Just kind of from... All right, so one of the things that we can do, given a connection, there is something called the affine parameter. All right, anytime that there is a connection on the space, so there are straight lines defined on the space, you can take a parameter along any given geodesic. You can parameterize the length of that geodesic. That parameter won't necessarily tell you anything about a neighboring geodesic, but it tells you about the length along that geodesic. For example, in free fall, I wear a watch. I look at the time going by my watch. Okay? That's a very good parameter to use. It's unequivocal. I'm in a free fall frame. I'm in an inertial frame. There's no reason I can't use the time of my watch as my parameter. If I'm accelerated, it's a little bit different. Okay? So, what would you say about the time on somebody free falling and the time somebody in a non-inertial frame? How do they compare? Will the time that he used, somebody here is like jumped up to the ceiling, was on the way up and the way down, whatever, and they're parameterizing their in a geodesic of space-time? I'm not. My time on my watch and their time on their watch. What's the relationship, just practically speaking? Same. Right? Nobody ever found a difference. Right? Measurable difference in the Newtonian regime. All right? So basically, it doesn't matter which parameter. Since he can use the proper time on his geodesic, the affine parameter on his geodesic, as the parameter for the geodesic equation, right? And since it's equal to the time of my watch, so we'll just switch that and make it second derivative of r with respect to my time. Okay? Again, this will work in the Newtonian regime. Obviously, if we're in extreme situations, very high speeds, very, very high masses or densities, and so on and so forth, you know, we're not in the Newtonian regime. We have no right to expect that those times will be equal. We have no experience with it. Okay. What about on the right-hand side of the equation? All that stuff. All that stuff has to boil down to one term. Now, it could be that it boils down to one term, that all those things superpose together and make one nice function, gm over r squared. But in fact, it turns out that there's one very specific piece of that geodesic equation that boils down to this. Okay, and that's on the pages. I don't know if we'll have enough time to go through it, but I'll hopefully just a few minutes to go through that. In the warp space, I'm going to have a geodesic equation, r double dot, where again, this is derivative with respect to a parameter, but in the end, I'm going to make it the parameter to be just ordinary time, so I'll leave it as r double dot. And you can either have equal to something or plus something equals 0, doesn't matter if you're counting this on the right-hand side or the left-hand side. Here, there will be a sum of terms. The terms will be, you're going to have, all the different coordinates are going to have like velocities here. You can have dr, d, whatever this parameter was, and d theta is, and you can have dr, dr, and you can have d theta, and let's say dt, and dt, dt. All right, if it's spherically symmetric, you're not going to have all kinds of mixed crazy terms, you know, theta, phi, theta, or something like that. You have always r's and so on. We're going to expect that in the time, space-time geodesic equation, where we're going to have terms like dt, dt, depending on what the parameter is here, right? dt the parameter times dt the parameter, dt the parameter times dr the parameter, d theta the parameter times dt the parameter, all these different mixes. And each one is going to have some coefficients. It's the sum of all these things, all these different terms in your geodesic equation. All right? Okay, that's familiar? That's just a straight line equation. But in a straight line, in perfect coordinates, you would have, let's say, theta double dot plus r theta square, I don't know, whatever is equal to 0, right? These things are the connection coefficients, and these things are the products of these little velocities. So in space-time, you can have the same thing, a product of these like velocities for all the different coordinates mixed with a coefficient in front. These coefficients are gammas. That's the symbol for these coefficients. Okay? And they're labeled by whatever these things here are, whatever these guys are. This is the r theta. If this is the r double dot, so we put the r on top of all of them. These are the gammas for the r geodesic equation. And the gammas for the r geodesic equation have one for the r theta mix, and one for the r mix, and one for the rt mix, and so on. So you end up getting all these gammas with 3 indices. These two are the ones that these velocities, right? And this one is the one, the coordinate whose geodesic equation we're taking. Okay? So that's all these things are. These things are the coefficients in the geodesic equation. What are they mathematically? They are the connection. The connection on the space tells you about straightness in the space, and the way that it tells you about straightness in terms of coordinates is it specifies all these different coefficients. So it's a geometrical object which has components, just like a vector has components. In the geodesic equation, these components work as coefficients of these velocity times velocity curves. It's the geodesic equation, but it looks like a curved world line equation, because that's r double dot, but it's the equation of a straight line. All right? But clearly it's this that's going to boil down to our r double dot equals gm over r squared. Somehow all of that has to boil down. Right? This boils down easily when we realize that we can use proper time as a parameter. It doesn't matter in ordinary gravitational Newtonian regime gravity. It doesn't matter if we use just our watch time, right? Even if we're standing on the planet. All right? As you can see, you can have a dt, and if this parameter is t, these are going to be 1 and 1. All right? And that's going to be like the largest and the one that remains. So you're going to end up with this gamma RTT is going to be the one that really determines what this geodesic equation looks like in the Newtonian regime. So this whole big equation will reduce to what? R double dot plus gamma RTT equals 0. Okay? This became 1. This became 1. The other ones don't contribute, and you get this. One can show why all of these things, most of these things drop out to 0. Okay, there are various reasons why all those things. For example, one of these things will mix r and t in a way that has to do with rotation. If the thing is not rotating, if it's just a static object, one of these will automatically go out. So one can show why this will, in fact, how it actually reduces. It's easier to do, in fact, if you use special relativity and so on and so forth. If you had a little more time, I would do it. But even without, you can show why this would, which terms it will be. The term that's going to remain, all right, ends up being this one. Okay? Connection coefficient here. This gamma RTT with 3 indices. Okay? This is the thing of which the one with 2 indices is the shadow. We're going to have a connection coefficient in this curved spacetime. That's going to be part of the geodesic equation. We're going to have r double dot plus this gamma and maybe some other things equals 0. And when we project that down to flat spacetime, so to speak, what we're going to end up with is r double dot plus the world line curvature equals 0. In other words, r double dot equals to the world line curvature, which is gm over r squared. Okay? All right? This is what? The curvature of the world line. Correct? All right? There's no symbol for that. I'm going to call it, because it's this thing that reduces down, I'm going to write the symbol as this. I'm going to call the curvature of the world line. I'll call it that. There's only two indices. To show that we understand that this is the flat space-time shadow of this thing. This is a curved space-time equation. There's a parameter here, right? That's not time. This is a curved space-time thing. But it's a curved space-time equation in the Newtonian regime where we were able to get rid of all the other guys. And these things approximately went to 1 because the time is a symmetric quantity, right? This is a flat space-time equation, all right? And this gives it away because this is a curved space-time quantity and this is a flat space-time quantity. Let's talk about the field equation. We have an idea of the equation of motion. What's going to happen to a particle in this warp time? We know that its world line is going to be a geometric of the curved or warped spacetime. We don't yet have a field equation. The field equation that we're going to develop will be based on what we know the field equation looks like from the perspective of flat spacetime. We need to have a field equation that describes how this warping takes place. We know we're describing gravity, so we know we're talking about mass as the source. All right? What kind of field equation can we create? Well, we'll start with gravity, namely A is equal to gm over r squared. Okay? We know that that's going to be a solution of the field equation. Instead of A is equal to gm over r squared, what is the differential version of that? A differential field equation of which this is the solution for this case. A is equal to gm over r squared. Do you know? Did you learn that in Newtonian gravity? The differential form of the field equation of which it is a solution is divergence of A equals rho, where rho is the density. If we're talking about outside a mass, and it's a local theory, the density is 0, divergence of A is equal to 0. And as we saw, the solution of that gives you some constant over r squared, so don't get frightened by the 0 on the right-hand side. It doesn't mean there's no phenomenon. It means that there's a constant over r squared. The constant would be 0 if there was no mass. The constant is gm if there is a mass. The lines of the theta and the phi coordinates, although they're theta and phi, their curvatures depend on r. Clearly, right? The bigger r is, right? The bigger the circle, the less curved it is, 1 over r. All right? So you have these connection curvatures, the connection coefficients, which tell you about the curvature of these coordinate lines, connection coefficients, which exist even in a flat space-time, in a flat surface, or a flat space, just at the curvilinear coordinates. They're labeled by coordinates theta and r. All right, so it'll be theta, theta, r. And phi, phi, r. All right? On one of the pages, I guess we don't have time to go through it, but the connection coefficient will be the one that tells you the connection between r and theta. All right? That's what tells you how this coordinate line curves and gives you the 1 over r. So we can write the divergence in terms of connection coefficients, these angular connection coefficients, right, 1 over r's. The divergence part of the equation I can write as derivative plus gamma r theta theta, gamma, right? We wrote it out explicitly, divergence of A is A prime plus 1 over RA equals 1 over RA. We recognize those 1 over r's as connection coefficients, which exist even in a flat space-time, in a flat surface, or a flat space, just at the curvilinear coordinates. In other words, if you have a theta and phi coordinate lines, which are circles, their curvature is 1 over r, right? So those 1 over r's come in. Instead of just being A prime, the derivative is A prime plus 1 over RA plus 1 over RA. So we're going to write those 1 over r's as connection coefficients. Now what we're going to do is write the acceleration equation, div A is equal to rho, and instead of this div, we're going to write it making explicit the fact that these are connection coefficients for the curvilinear coordinates. The 1 over r's are these gamma r thetas. That's just ordinary curvilinear coordinate connection coefficients. No curved space-time in here, nothing at all. All right? So we have the divergence of A is equal to rho. The divergence part of the equation I can write as derivative plus gamma r theta theta. So we can write, instead of div A equals rho, we can write div divergence of the world line curvature equals rho. Okay, is that step clear? Why I'm doing that? Divergence of, instead of acceleration, I'm calling it world line curvature. This gamma with an r and a t. A I know is world line curvature, so I'm labeling it as gamma RT because I know that it's a shadow of something that has to do with gammas in the geodesic equation of the curved spacetime. Okay? Divergence of the world line curvature equals 0. That's our field equation, ordinary Newtonian field equation, just in a differential version with divergence and seeing it as a world line curvature. So we have a space-time version. You have divergence of this gamma with an r and a t. Okay, you'll see the equation, the first equation. So I'm writing a purely Newtonian flat theory. Okay, there's no curved spacetime here. I have a divergence, just ordinary divergence, of the world line curvature. No curved spacetime in there. And it's equal to the derivative plus 2 times 1 over r times a. Times a, that's simply the ordinary divergence for curvilinear coordinates. And I'm operating on A, but A I know is a world line curvature, so I'm labeling it as gamma RT because I know that it's a shadow of something that has to do with gammas in the geodesic equation of the curved spacetime. Okay? Now, this equation is a very geometric one. So now if we write it explicitly, we're going to have the derivative with respect to r plus gamma r theta theta plus gamma r phi phi operating on gamma RT. That's our field equation. That equals rho. Got it? This is the divergence, and this is the thing that it's operating on. If we write it out more explicitly, we'll just get d derivative with respect to r of this guy plus gamma r theta theta gamma RT plus gamma r phi phi gamma RT equals rho. If I just multiply them out, I get derivative of this gamma RT plus gamma gamma plus gamma gamma equals rho. Or if I'm in vacuum, it's equal to 0. Okay, now look at that equation carefully. Tell me if you don't understand something. This is a purely flat, not even space-time. It's space-time, but it's just ordinary Newtonian. There's nothing here beyond Newtonian theory. Okay, I want you to be convinced of that. All right, does anybody see something that looks that this is not Newtonian theory or doesn't understand where it comes from to begin with? Tell me now because we're going to build on it. We can write A also as a connection coefficient. Why? Why do I say that A is a connection coefficient? How did we start our mapping? What are we looking for? What are we looking to map? We know that the gravitational acceleration is the flat space-time world line curvature, and that is somehow a shadow of something that exists really in curved space-time. What is it a shadow of? What curved space-time quantity is it a shadow of? Okay? We have a geodesic equation. The geodesic equation has the second derivative of, let's say, r with respect to a parameter, which we're going to be able to choose as time, as we said. And that's going to be equal to a whole bunch of things depending on connection coefficients, which define the geodesic for a warped spacetime. We expect that that whole equation is going to boil down to this r double dot is equal to gm over r squared. Okay? A real connection coefficient here. This gamma RTT with 3 indices. Okay? This is the thing of which the one with 2 indices is the shadow. What do we have to change in there? What is inherently flat space-time?
The coefficients.
The angular thing will still be, if you have spherical symmetry, is still going to be the same 1 over r. The space-time part, the time thing, this gamma RT, the world line curvature, is a reflection of this connection coefficient. So we're now just going to stick it into the equation, but it's the same equation. Just that now we're reinterpreting this equation. Instead of an equation for the acceleration, it's an equation for the connection coefficient. So we're speculating now. We're going to speculate and say, you know what? This is such a geometric equation, and this talks about connection coefficients. Maybe the curved space-time equation is the same thing, just instead of this gamma RT, it's this. We're going to write it making explicit that this acceleration is what? It's a world line curvature, which is a reflection, a shadow of this guy. Okay? Questions? Start over from the beginning?
No, it's good.
Good? You got it? Okay. Okay? And that's the equations on this page. All right, if you look at equation 1 and 3. Got it?
Divergence by itself is a very geometric equation, but it's geometric also because it's all connection coefficients in there. Derivatives and connection coefficients. Two different types of connection coefficients. One, ordinary curvilinear coordinates for free space, like the 1 over r's, which are these gamma r thetas. And another connection coefficient, this gamma rt, it's actually it's not a connection coefficient, it's a world line curvature, it's a reflection of a connection coefficient. All right? So it's a very natural thing to imagine. Look at equation 3 further below. It's simple to imagine the possibility that this flat space-time gravity equation is a shadow of the equation 3, where in equation 3, all these quantities are meant to be in curved space-time. We'll have to define the divergence for curved space-time, but this was a divergence up here for curvilinear coordinates, and the curved space-time that we're defining is based on the same definitions as for curvilinear coordinates or curved surfaces. And it has a gamma, but the operator is operating on a real connection coefficient here. This gamma RTT with 3 indices. Okay? This is the thing of which the 1 with 2 indices is the shadow. All right. We have a problem now, though. All of this was based on the equivalence principle. The equivalence principle tells us that if you're in a free fall frame, you're inertial. As long as you're in that inertial frame, you don't feel anything. You can deny that there's gravity operating. There's no way to prove, just like if you're in a plane, you're moving at 600 miles an hour, the thing doesn't slosh. No one can prove to you from instruments located inside the plane that you're actually moving, right? In the same way, in a free fall frame, no one can prove to you that you're actually accelerating. Therefore, you have no theory. You have no phenomenon. So the equivalence principle helped us build this whole theory, and it destroys the whole theory at the same time. There is no phenomenon. We just got to erase this whole thing. So the equivalence principle helped us build this whole theory, and it destroys the whole theory at the same time. There is no phenomenon. We just got to erase this whole thing. Of course, we have an intuition that's not so. How do we rescue the theory? Challenge.
We look from the outside of the plane.
Local. Physics says if you can't tell locally, then, you know, it's not a real phenomenon. There's something happening, but it's not what you think. How come, is there any phenomenon? Maybe there isn't. I don't know. Is there a phenomenon? Do you agree with me that you're in free fall, you don't feel accelerations? Agreed? Yeah. Some people will go either way, right? No? Okay. So if we don't feel accelerations, is there some phenomena or none? Does anybody think of a phenomenon that might? Maybe there isn't. I don't know. I mean, if we take the equivalence principle seriously, there should be a phenomenon, right? You can't tell that you're in a free fall frame.
Maybe there is another object in this formula that we didn't.
Well, say physically speaking, it has to be a physical phenomenon. Is there any physical phenomenon in a free fall frame? There's no gravitational acceleration that we know. It's got to be something to do with gravity. I'm not talking about electromagnetism. So if there's no gravitational acceleration, does that mean by definition there isn't anything? The answer is that we need more than one particle to discover. Okay? If you have two particles falling, let's say alongside each other or one on top of the other what will happen?
See different acceleration.
Pardon me?
You see them like go apart.
Okay, why? Obviously because
For the different places.
one is closer to the source than the other, so this has a higher acceleration. So this was accelerating more. So from a free fall frame, what you'll see is the two moving apart. What about these two? These two obviously get closer, but that's nothing unusual. I mean, just two things moving at a constant velocity this way will get closer to it. That's nothing to do with gravity.
The rate that they're getting closer is changing.
Why?
They're accelerating.
Why? Is it true? Are they?
It depends where.
So the thing is, if they're accelerating in this direction, then the separation between them also accelerates. Okay? Let's look at all these accelerations. They're definitely measurable. They're physical quantities. They have directionality, but not like a vector. This is not a vector. And they're also all these different quantities related to at a point. This is called tidal acceleration, right? Relative acceleration. And we measure it at a point, meaning take a point, take some particles near the point, around the point, whatever measures you get are associated to the point. So at each point, there's really a tensor. Tensor because you have directionality, but it's not like this or like that. It's a relative thing. And there's 6 of them or more or whatever, depends, or 3, right, at a point rather than, one thing at a point in one direction. All right? So there is a tidal tensor that's observable in a free fall frame, not at a point, obviously, but a little bit more than a point, in a local region more than a point. All right? So maybe there is a phenomenon. Maybe we can rescue all this, right? Maybe it works. How would we model that phenomenon? Does that have anything at all to do with space-time warping, curvature, something like that? Or is it just a totally new theory? What do you think?
You can see by how the extent of local changing in.
What do you see from that?
Sorry?
What do you see from that?
No, we can now somehow correlate this to the space.
Well, why would we think of this as a space-time theory or a curvature theory? We have tidal accelerations. Everybody knew about tidal accelerations. But we already thought to think of this as a space-time or space-time curvature.
You need to take use the formulation that you made and make two dots very close and makes the difference between them.
Right, and what will you get? We're talking about the difference between them. We're talking about the acceleration between them.
Yeah, so if you check the difference between them, you can see how the geodesics how it's act.
Okay, you mentioned a word that's important, the geodesic. All right, if we're using the equivalence principle to say that there's no acceleration in the free fall frame, and that's why we're looking at this and we discovered the tidal acceleration. So we have the acceleration, the equivalence principle built in here. But the equivalence principle also tells us that each of these particles is inertial. So what does that add? I'm telling you that all these particles are inertial.
The word line.
Put those pieces of information together, everything we just said, plus that their world lines are inertial. They are inertial, therefore they are inertial world lines. What are inertial world lines? They are geodesics of spacetime. All right? So now, think of these particles accelerating towards or away from each other. All right? Now think of their world lines. All right? Let's say these two particles are moving towards each other. Okay? So if you have its world line, the world lines basically, if you imagine the world line is just the time extension of these particles, the world lines will be getting closer and closer together. Spatially close. The spatial part will get closer and closer together. The closeness will be accelerated, just like the two particles are accelerating. If you take a parameter along these geodesic world lines, right, and you measure the distance between them relative to this parameter, there will be an acceleration of the separation. Can that happen on a flat surface, let's say? Take two geodesics, right? Let's say two geodesics that are moving towards each other like this. What will the separation be relative to a parameter? Constant velocity, right? It'll change, but at a constant rate. It cannot be that there will be an acceleration relative to the parameter. If there's acceleration relative to the parameter, something is, it can't be geodesics, or there can't be a flat surface or flat spacetime. All right, so if we take seriously the equivalence principle, we end up with world lines, free-fall world lines being geodesics of spacetime. We end up with this whole picture, which we then have to overthrow because we don't have phenomena. We then find that tidal acceleration, taking this equivalence principle seriously, tells us that these geodesics are what's called deviating. They're experiencing like deviant behavior. They're deviating from each other in a way that you wouldn't expect geodesics, at least in a flat space, flat surface. So this tells us that there is curvature. This type of curvature is a higher level curvature, so to speak, than the type that we were talking about before. The type that we talked before is potentially spurious. If you go on a free fall frame, it disappears. This exists even in a free fall frame. The definition, if you write down, and again these are on the papers that I gave out, if you write an equation for the separation vector, you find that there's a second derivative of the separation vector with respect to some parameter. It turns out to be proportional in some way to the separation, the second derivative. These things are the Riemann tensor components. That's like a way to define what the Riemann tensor components are. They are the things that tell you how to write this equation. What is the proportionality between the acceleration, the second derivative, and this guy over here? And it's a remarkable equation because it's kind of like linear in these things. It's not derivatives of these guys, whatever. All right? But that's one way of defining what curvature means. Curvature is when there is deviation of geodesics. What is the Riemann tensor? It's the tensor whose components tell you these things. Just like what is the connection? Its components are coefficients in the geodesic equation. Okay? Now there's a nice way also of seeing that there is curvature in a global sense. Two geodesics on a flat surface can certainly cross. They can certainly not cross twice. Do you agree? Once they've crossed, they can never come back and cross again. If they do, we have curvature. Can anybody think of an example in gravity, just purely ordinary gravity? No space-time, curvature, nothing. Where world lines, so it's flat space-time, let's say, world lines meet twice of free particles. What?
Two particles orbiting the same.
Okay, how are they orbiting, right? How are they orbiting?
One is the other.
One is what?
One is orbiting on a plane and the other on another plane.
Okay, so one is going like this and one is going like this. They intersect twice. So we say, oh, of course they intersect twice. So what? So again, why is that significant? Because each of those is a free fall, right? Each of those is a free fall particle whose world line is a geodesic of spacetime. This is not a geodesic of spacetime. This is a trajectory in space. If we drew the spacetime, right, world line, right, Of course, we're drawing it in a flat space-time diagram. It doesn't look like a geodesic at all. If we were able to draw a curved world space-time, we would see that it wouldn't look like it would be a geodesic, right? Just like if you had a curved surface, that's a geodesic, okay? And you have two geodesics. This guy's world line, which is not this is a trajectory, and this guy's world line, which is not this is a trajectory, they meet twice. Obviously, if the trajectories meet twice, the world lines will meet twice. But the fact that the trajectories meet twice is not the significant thing. It tells you that the world lines will meet twice, and that's the significant thing. But even that is not significant unless they are both geodesics. Since they are both geodesics and they meet twice, it's got to be a curved space that they are geodesics of. They can't be geodesics of a flat space. So if we take it seriously that these are geodesics of space-time is curved. There are other examples. For example, one famous one you have, let's say in the Earth, you draw a core, a hole, tunnel all the way through, you drop a particle, it speeds up and then slows down as it gets further away from the center, speeds up, right? Oscillates back and forth. Take another one, drop it over here, they're going to meet many times. All right? Polar launch was another example that I've seen. If you launch a projectile from one pole to the other pole, or from any place on the Earth to a place, polarly opposite to it, right? Then, and from this one to this one, okay? So, sorry, if you launch it in two different directions like this, okay? You launch it from pole in this direction and they meet here. They start off and end off meeting. So that means that their world lines met twice, which means space-time is curved. Okay? But that's a non-local way of seeing it, and we want to do it locally, which is the way that we said in these tidal accelerations. So now we can legitimately see the tidal accelerations as shadows of curved space-time quantities. In the same way that we saw earlier the gravitational acceleration as being the shadow of a curved space-time quantity, we now see a somewhat more sophisticated version of the theory where the tidal accelerations are the real arbiter, they're the real indicators of curvature, and they are reflections of basically the Riemann tensor components. And you can see that on the paper. Right, at the bottom of the picture of the diamond, take 6 neighboring particles infalling the diamond shape, and I just made up a notation for the relative accelerations, these tidal accelerations, the RTR, the RT theta, and the RT phi. I added T in there because I know that these have to do with space-time and world lines and curvature of world lines and so on. So these are tidal accelerations, but I know that they have to do with time somehow. So I'm adding the T in there. It's the R, the theta, and the phi pieces. The tidal accelerations are the real arbiter, they're the real indicators of curvature, and they are reflections of basically the Riemann tensor components. So now we want to have a field equation for the real quantities. We had a field equation for the acceleration, but the acceleration disappears, so we don't want a field equation for things that vanish. We need a field equation for the things that you can actually measure, which are the tidal accelerations in the Newtonian picture, or the Riemann tensor components in the curved spacetime picture. All right? So how do we come up with a field equation? You have a little experience now with building field equations for curved spacetime. We did it for accelerations. How we... If I order more pizza, okay, any ideas? What we'll do is we'll model it on the gravity equations. So we have to have a gravity equation for tidal acceleration. So let's try make a gravity acceleration for tidal equation and lift it up kind of to a curved spacetime interpretation. All right, so we have these, in this very highly spherically symmetric case, right, we have 1, 2, 3 things. These two, obviously, through spherical symmetry will be the same. These two angular things, and there'll be a radial thing here. Okay? So we have these three things. They're associated to each point. They're real measurable quantities. A field equation has to tell us about real physical measurable quantities. It can't skip out some of them. It's got to deal with all of them. If the only thing that we have is a scalar function, the density, we're going to be in trouble. In fact, if the density is 0 outside in a vacuum, we're going to have on the left-hand side something and the right-hand side 0. When we had a differential equation, it was okay. But if we just set, for example, the tidal, this tidal thing equals 0, well, nothing. This tidal equals 0, nothing. A way of getting around it would be to take a sum. Because really all these things are talking about one point. If we take the average of these things, of the tidal accelerations, right? And that characterizes the point, and it's that which is determined by the scalar function rho. All right, that's a way of getting around the problem. And it's actually, if you're adding these three pieces, right, this is the r and the theta and the phi, those are actually the diagonal components of the tidal tensor. So you're taking the trace. You're summing these three components on the diagonal. All right? So we're going to have a tidal acceleration equation, okay? You have three different pieces. Two of them are equal to the angular. I add them up equal to rho, or in vacuum, equal to 0. All right? And I added them up. The sum of those three I labeled as r with just one t on top. We don't have the problem that they all equal 0 because we made the sum of it equal 0. Right? The sum vanishes, not each one vanishing. But we still have two things to determine with only one field equation, with one quantity on the right-hand side. All right? However, we can be rescued by something because we know that these tidal accelerations are built up of what? How do you determine these tidal accelerations? Well, the acceleration here and the acceleration here are different. It's really the derivative of the acceleration, how the acceleration changes along this direction. That's what gives you the relative acceleration. Correct? What gives you the relative acceleration of these two? They're at the same location, so their acceleration is the same. It can't be the derivative of a. If you work it out purely in Newtonian gravity, it's 1 over r times a. The acceleration, the relative acceleration in this direction of these two things depends on the fact that these are accelerating this way. If there wasn't acceleration radially, they would not have a tidal acceleration in this direction, correct? So it's dependent on a. It's also dependent on the connection coefficient 1 over r, the curvature of this thing. So the three tidal components are a prime, 1 over r a, 1 over r a. Those are the three tidal acceleration components. If we make an average, it's a prime plus 1 over r a plus 1 over r a. We'll set that equal to rho. Okay? So that would be our tidal field equation. And that's at the bottom of the page. All right? Now instead of a prime and 1 over r times a, I'm calling a the world line curvature. Again, still Newtonian flat spacetime. World line curvature is Newtonian flat spacetime. These 1 over r a are just Newtonian tidal accelerations. Nothing, no curved spacetime. So at the bottom of the page, above equation 2a, you have the r part is the derivative of the world line curvature. The theta part is 1 over r times the world line curvature, and the phi is also 1 over r times the world line curvature. The sum or average is these three things together is this. Now what does that look like? What does that equation look like? We saw it before, like on the upper left-hand side, what? It's exactly what we got as the field equation for the acceleration, for the connection. Exactly the same equation. Okay, so we don't even have to come up with a new equation. When we came up with this equation, it turns out to be the same thing, which means also that there's a substructure. The tidal acceleration has as a substructure the gravitational acceleration. The tidal acceleration field equation turns out to be an equation because of this substructure that describes the acceleration. It's really a tidal field equation, but since the tidal field equation has a substructure, the gravitational acceleration, it turns out to be a gravitational field acceleration equation. All right? So now we're tempted to say, let's interpret that as a curved space-time. This was all, again, flat space-time, Newtonian gravity. We're now going to say, let's interpret that as a curved space-time equation. By, how do we do that? How are we going to adapt this equation to be curved space-time? What do we do? We turn over the page, right? What do we do? It's an equation for the Riemann curvature. And we're adding up 3 different Riemann tensor components, like the 3 different tidal components, and we're getting a trace, kind of a trace of the Riemann tensor, which is, if you know, you already studied this, so you're contracting over the indices, and you're getting a different tensor, it's the Ricci tensor. But it's the same equation, I mean, we did that already. We're just doing what we did before. Just that now we're reinterpreting this equation. Instead of an equation for the acceleration or an equation for the connection coefficient, this whole thing is a Riemann curvature whose substructure is connection coefficients. Just like the equation for the tidal acceleration whose substructure is the gravitational acceleration. Okay, so this is the Ricci tensor for this highly symmetric situation in the Newtonian limit and so on. All right? And in fact, if you work out the actual calculations, you'll find that they're very similar. This is like the core of the Riemann tensor components. All right? If you choose Schwarzschild coordinates and so on. What you're going to find is that you have to neglect a little piece of the Riemann tensor components to get this. And that's where we go now to the third piece. I know I'm going to end soon because I know this is, we're getting late, but and in fact, it turns out to be almost exactly that for a particular coordinate choice and so on. If you solve the Schwarzschild and you got the Ricci, what is Ricci? Ricci is the sum of Riemann tensor components, right? That's what this is. We'll get to that in a minute. So this is really very, very, very similar to the real exact solution for when we use Schwarzschild coordinates, which is a very natural coordinate system to use. Now, we're going to end up with the same problem as before. We have a field equation, but we don't have enough information to solve it. We have these at least 3 Riemann tensor component pieces, and really, you know that if it's going to be less symmetric, there are going to be many more. All right, you have the whole tensor, the second rank tensor in 4 dimensions, right? So we're not going to solve it with just a scalar on the right-hand side. Clearly, we're going to have more. I mean, if you have a tensor on the side, you know you're going to have a tensor, whatever. It's certainly going to be, you don't have to know general relativity or special relativity to realize that you're building, excuse me, tensor equations over here. You're going to need tensors on the right-hand side. But even before we get that, the way around the problem that we experienced before, where we had these connection coefficients, and it wasn't sufficient to solve the field equation, right? We had too many. We had these things, the same equation. We had too many things to be specified by this. We know that these are 1 over r, right? In this sense, we know, okay, we know this is gamma RT, maybe we can solve this over here. In this case, maybe we have enough. But if we have 3 different Riemann tensor components, even though 2 are the same because of spherical symmetry, we still have 2, this and one of these guys has to be specified. How could we possibly go about solving that problem? What could there be, based on experience with building this model? What might there be that would help us solve this? Not only to solve this, but it addresses something that we skipped over that some people actually asked about, and I said, oh, that's later. Again, I'm not making the question too clear because I don't want to give away the answer, but what would save the day that kind of saved the day before? And the answer is substructure, right? we found an additional level of structure before. We had the connection, and we found that it's really the Riemann tensor, and it's the substructure of the Riemann tensor that we were dealing with, right? There's actually an additional level of structure in this whole theory. All right, we had two levels. We had Riemann tensor and the tidal acceleration. What was the flat space-time shadow of the Riemann tensor? Tidal acceleration, or tidal acceleration tensor. What was the flat space-time shadow of the connection? The acceleration. All right? It turns out there's another level of structure which corresponds this way and this way. All right? Where would there be a hint maybe to another level of structure? So actually there are a lot of hints. Again, these hints are only post facto, right? Not something that somebody looking at the theory would immediately recognize. We can either look at differential geometry, since we see that we're building a theory based on differential geometry, and learn a little bit more differential geometry, and then we would recognize some feature in gravity. Or we can investigate gravity and then try to model it with differential geometry. Okay? Now, one of the things in differential geometry that one knows of has very much to do with the very underlying feature that we spoke about at the very, very, very beginning, this warping of time. And I said it wasn't the curving. Okay? There's a way of seeing what it actually is. Okay, and that's on one of the pages that I gave out to you. All right? Does anybody know if you solve the equation r double dot equals gm over r squared, and you want to find the world line equation in flat spacetime, r of t. What is r of t? What's the equation for r of t? Just in ordinary gravity, gm over r squared. What is it?
Ellipse.
Okay, what's the formula? Has anybody ever seen it? Okay, you have it worked out over there. It's t to the 2/3. R is t to the 2/3. That's simple calculus. If you take the second derivative of t to the 2/3, you end up with 1 over r squared. Okay, and this is a very important equation. In general relativity, for example, collapse to a black hole is governed by that. The Big Bang expansion, if you want to find the age of the Big Bang, this what turns up. So this t to the 2/3 comes up all over the place. All right, so you have this page. You can just see it's just ordinary calculus just to find the solution of r double dot equals 1 over r squared. Simple differential equation. All right, if you substitute t to the power n, which I give as an example, you find that n is equal to 2/3. All right, so according to the equivalence principle, we would expect that in free fall, you have a straight world line. It should just be r is equal to t, or r is equal to at plus b, or whatever it is, right? We know, however, that it's really t to the 2/3. If you take the equivalence principle seriously, you're going to say that there's somehow some kind of stretching of time in this perspective. That t became t to the 2/3. All right? You can work out at home the ramifications of this t to the 2/3. All right? So now we're taking it seriously. We have a time measure difference. In differential geometry terms, what we have is a metric measurement of time. Rather than having just delta t, we're going to have some function which depends on your closeness to the source times delta t. Some f of r times delta t. If you end up, but just looking, without looking at the actual equation, if you just say, well, t is stretched, it becomes a function of t. Obviously, the way that I measure time in a gravitational source is different than the way that I should measure time in empty space. And if you look at this calculation at home, you'll see what that function of r should be. If you look at the calculation that I gave for the t to the 2/3 thing, you'll see that this function, just from that calculation without general relativity, turns out to be 2gm over b, and it turns out to be exactly the one that you find when you solve Schwarzschild and so on. All right? Clearly, this difference is not so big that we would have noticed it, because Newtonian gravity doesn't, know of such a, nobody knows of such a phenomenon. All right? So in the Newtonian regime, this effect is very small. So how could it be that this effect underlies gravity? I mean, people get hurt, right? They fall from a distance. Gravity, we feel it. How could this tiny, non-measurable time difference underlie something that clearly has a very strong effect? Challenge? Anybody think of a way? Okay, what is this acceleration? The acceleration comes about in the geodesic equation. There's going to be factors in there that relate to the scale of space and time. Okay, without knowing the scale of space to time, there's a lot of things that are hard to define. All right, we won't get into that right now. But the bottom line is, although the time difference is very small, like we said, we can use the proper time and the time on standing here on the surface, and it doesn't matter, right? The time difference is very, very small, but the effect of that time difference gets magnified in the geodesic equation. So you get a real acceleration that we can measure. Okay, and that has to do with factors of c and so on. So we now have a suspicion that maybe underlying all this is something to do with the time measurement, like a metric. If you look at differential geometry, you find that some spaces have metrics, some spaces don't. You can have a space that has a connection. If it has a non-trivial connection, there will be a Riemann curvature. There does not necessarily have to be a metric. Now we know that space has a metric, obviously. We know that time has a metric. We don't necessarily know that space-time has a metric. In other words, we have defined parallel lines, straight lines in space-time using physics dynamics. We would have to think of some way that physics can tell us that there is meaning to the distance, the space-time distance between two space-time points. I mean, if I'm here now and I go to a different town in 2 hours, what is the space-time difference between those two events? I can say, well, it's 100 kilometers plus 2 hours, or 100 square plus. That doesn't mean anything. I didn't use different units. It's different, and it's just arbitrary. What does it mean? It doesn't mean anything. We gave meaning to straight lines in space-time. We would have to be able to give physical meaning to the distance between two space-time points if we want to say that there's a space-time metric. Okay, so the fact that there's a spatial metric and a time metric is a hint that maybe there's a space-time metric, but it doesn't mean that there is. Now we have a hint that there's a non-trivial time metric. But we can't really give meaning to a non-trivial time metric by itself. Just changing a parameter along the time axis by itself won't do anything. It has to be changed relative to something else. Just like we found, you always need space as a background to give you the context. It's space-time. The time is warped in the context of space-time. All right? So we have a non-trivial time metric. We can only give that meaning if we tack on to that a spatial metric. The spatial metric part doesn't have to be non-trivial. We just have like the time metric non-trivial. But it can't be by itself. And in fact, this is what Einstein suggested in 1913 before his 1915 complete theory, a theory of time warping where the metric, space-time metric, had a function only in the time part. If you look it up, it's E-N-T-W-U-R-F, entwurf. Okay, the entwurf-metric, entwurf paper 1913. And he had some function of r, dt squared, plus just a regular flat free space. The r squared plus r squared sine squared the things, whatever. Okay? That really is a good model of Newtonian gravity. It's not covariant, it has other problems and so on, but it pretty much gives you Newtonian gravity. We built it up from Newtonian gravity. Okay? Rather than postulating, in many textbooks they say space-time is a four-dimensional Riemannian manifold with a metric that is not a signature. That's true, it's very nice. And then you can work out the ramifications of that. In a way, it's a surprise when you solve the field equations and reduce it using the special relativity limit, and lo and behold, then you find gravity. Right? What we're doing is we're building up from Newtonian gravity and seeing that this is what's to be expected, really. It's still not, it's just a heuristic theory. It's a motivation to create that. Now we say, oh, you know what? Let's start. Space-time is a four-dimensional. Now that makes sense. Okay? There are other motivations to say that there is a metric underlying space-time. For example, these things come from a metric. And one of the pages I gave out was how you define, how you find the connection coefficients if there is a metric. Like three-dimensional space has a regular metric. The page that has ds squared on the top. Or I think we just had a look at it before. ds squared equals on the top. So that shows the rule of how you find the connection coefficients just for regular free space. in Cartesian coordinates where these coefficients vanish, or in polar coordinates where they don't vanish. You get these 1 over r's. All right? So these things, the theta 1 and the phi 1, obviously are based on a metric coefficient. So we can write this in a little bit more sophisticated way with g's in here, these metric coefficients under g primes, which again gives us a reason to suspect, since they're all connections here and these are metric connections, maybe the space-time thingy is a metric connection. All right? Make the calculations much more simpler. If you look at the energy conservation equation, the energy conservation equation, again, is one of the pages I gave out, can kind of heuristically very easily be turned into a metric equation. For example, I'll just do an outline over here.
If you need more,
I can raise this, right, yeah. You're right, thanks. V squared plus phi equals constant. And you end up using 2 of the basic features of gravity. One, the equivalence principle. So you're not going to be talking about forces or potential energies, but you're going to be talking about velocity and potential. All right? You're talking about velocity rather than forces, get v squared. And we don't have to write the gravitational acceleration. We can write it, it's equal to phi, right? So this is the gravitational energy conservation equation, written with these 2 principles manifest. Okay? This is like dx dt squared plus phi equals k. If we multiply all of this through by dt squared, we get something like dx squared plus phi dt squared is equal to k dt squared. We put these 2 together, we get something like this. A flat space with something happening at a time. There are all these little hints in gravity to the fact that there's this non-trivial time. And what is it related to? The potential. How do we know that it's related to the potential? Because we can make this little chart over here. We have the Riemann tensor components whose shadow are the what? The tidal accelerations. Okay? I call those things R with a bar. There's only 2 instead of 4. This has as its substructure what? The connection coefficients. Right? 3. Whose shadow is in flat space-time is the acceleration. This, we know from differential geometry, is constructed out of the metric. That's how you get these things from the metric. Automatically, knowing that this is g prime over 2g, we're going to suspect that the shadow thing over here is going to be something whose derivative is the acceleration. Now, if we know gravity, then what we know is the potential. So this is our chart of Newtonian gravity and general relativity. Again, tidal acceleration constructed of the gravitational acceleration, constructed out of the potential. In general relativity, the Riemann tensor constructed out of the connection, constructed out of the metric, and then cross in this direction, this, the shadow of this is the shadow of this, the flat space-time shadow of that. Okay? If we want to make a metric, we're going to square it and add it to the other things, right? We're going to have just flat free space, just ordinary. We had no reason to make this anything over here. This was just to give us context. But here we're going to have some function of r. Now this has to reduce to 1 in the end, right? If there's no gravitational field, if there's no mass, we want this to be 1, not 0. So it'll be something like that. Of course, we know that there's supposed to be a signature thing here that's a little bit more complicated. We may or may not be able to find that out with special relativity. It's possible that we maybe, by the fact that gravity is attractive, maybe that would give us a hint and so on. But the bottom line is, we're led pretty much purely from gravity and understanding of differential geometry to see this as a model of gravity. How does it model gravity? This is a connection, this is a metric coefficient. Take its derivative over that and you get a connection coefficient. Stick this in the geodesic equation and you have a geodesic equation, meaning free particles have world lines which are geodesics, and the geodesic, the description of the geodesic will have this guy in it, derivative of this guy in it. So you have a mass, it gives rise to a potential. That function describing the potential is actually a metric coefficient for the time in this warped time spacetime. That is going to appear, it's not so strong that it's noticeable, let's say in the Newtonian regime, but its derivative and other things and so on gives you these connection coefficients, which when placed in the geodesic equation results in an equation that looks very much like the Newtonian acceleration. Basically it is r double dot equals g over r squared. If you look at the calculation that I gave for the t to the 2/3 thing, you'll see that this function, just from that calculation without general relativity, turns out to be 2gm over r, which is in fact the Schwarzschild solution. And this is the metric that Einstein gave in 1913. The paper is called Untitled Chapter, ENTWR. You can find it easily.